The clue is in flapping flight propulsion, which is actually very well designed and optimized for dealing with wind turbulence. A lot of the birds and insects have extremely elegant and subtle strategies for tolerating gusts in a way that a rotary propeller cannot.
You're listening to the Drone Radio Show podcast, the show about drones and the people who use them for business, fun, and research. Hosted by Randy Goers.
Hello, everyone. This is Randy Goers, and welcome to the Drone Radio Show podcast, episode 103. Can we learn anything from a Dragonfly about making a better drone? If you ask today's guest, he would say we already have. Alex Caccia is a serial entrepreneur with startups in hardware, software, and sports equipment. He is also the CEO of Animal Dynamics, a spin-out company from the Department of Zoology at Oxford University. Animal Dynamics is developing a portfolio of products derived from research into evolutionary adaptations in flight, swimming, and walking based on the movements of high-performance animals. Their current project, the Skeer drone, is a micro-drone with flapping wings based on a dragonfly. In this episode, Alex talks about animal dynamics, the science behind looking at high-performance animals, the Skeer drone, and the role of university-based research in launching new technologies. Before we hear from Alex, I want to thank all of you who have supported the show's fundraising efforts on Patreon. This podcast is free, but there are production costs, and Patreon provides an easy way for listeners to support the show. Go to patreon.com/drone radio show to join the team. And again, thanks. Okay, so let's find out how a Dragonfly is the inspiration for a new class of drones. Let's pick up the interview where I asked Alex to introduce himself.
My name is Alex Caccia. I'm CEO and co-founder of Animal Dynamics. And we are a spin-out company from Oxford University. We're specializing in propulsion systems based on natural systems. So we're looking at ways in which movement in nature has resulted in surprising gains in performance and efficiency. And so what we're looking at in particular is flapping flight, the way fish and cetaceans swim, and certain kind of walking kinematics that provide sort of unusual efficiency profiles.
So do you start with animals and try to understand what makes them move, and then you develop a product? Or do you start with the product idea and then look back to an animal that is related to it?
Well, it's all a bit messy, frankly speaking. I mean, more often than not, we start with a need, a market requirement, and then we go and look and say, is there something in the natural world that can help us solve that problem? So to give you an example, I mean, the main project we're working on right now is a small-scale drone called Skeer. That's our name for it at the moment. And the sort of challenging thing about it is that we've been asked to build a drone that is around about the sort of 120 millimeter length, so really quite small, but that can tolerate high wind conditions and is quiet and stealthy. Because the reason behind that is that existing drone technology really struggles to deal with wind turbulence, particularly when our platform gets smaller. But if you ever go out on a windy day, you can see birds and insects kind of getting on with their business, not really minding it in any way at all. And the clue is in flapping flight propulsion, which is actually very well designed and optimized for dealing with wind turbulence. A lot of the birds and insects have extremely elegant and subtle strategies for tolerating gusts in a way that a rotary propeller cannot. And there are some fundamental design limitations with rotary propellers, the most obvious of which is that when moving forward, the attacking blade creates more lift than the retreating blade. So you have an inherent instability. And of course, that becomes accentuated in turbulent conditions. And all the numbers get worse when you get smaller, largely because the inertia is quite an important factor. In helicopter design, the available inertia decreases very rapidly as the size decreases. And therefore, you lose that damping factor. And then, of course, all the aerodynamic numbers change as the Reynolds number changes when you get smaller. So making something small and gust tolerant is a really interesting challenge, and it's clearly looking at how nature does it is a good place to start.
Which animal, bird, or insect are you using as the model for the Skeer drone?
Well, we're looking at dragonflies in particular for a number of reasons, one of which is my co-founder, Professor Adrian Thomas, who's Professor of Biomechanics at the Zoology Department here at Oxford, has studied dragonflies for many years and has a deep understanding of dragonfly flight. They have some very interesting characteristics. For one, when the wings are fixed, they can glide, and we've made little small gliding dragonfly-like things. That's a huge advantage when you're looking at drones because most quadcopters can't glide. Secondly, they are extremely high performance, even in the insect world. Dragonflies are probably the world's and nature's most successful predator in terms of kills as a percentage of attacks. And that's because they've got enormously flexible wings. And in terms of scale, they're about the right scale for us. And the useful thing, of course, with four wings is it gives you pitch stability. So you can have a flapping-only architecture, which is something that we're keen to achieve. So there are sort of good structural reasons why dragonflies is an interesting place to look. And we've got lots of data on dragonfly flight and wing design and so forth, which we can refer to in our designs.
When I think about how a dragonfly looks and how they work, it just seems really complicated to try to bring that into our environment where you have to manufacture the components, especially at such a small scale. Obviously, you guys have looked at this, but what are some of the design challenges that you have to solve?
I mean, yes, it's complicated, and we sort of have to look at everything from first principles. But the encouraging thing is it can be done because they do it. In the project we had, we spent a goodly amount of time doing a kind of feasibility study, really asking fundamental questions such as, can we design motors that will produce sufficient power in order to power a device like this? Can we miniaturize the electronics and get the weight and payload down to a level that makes it feasible? One of the most important things is wings. The dragonfly wings are a thing of absolute beauty, but we have a huge advantage over them in as much as dragonfly wings are made basically of an equivalent material would be meringue, in other words, protein and sugar mixture. We can use all sorts of fantastic materials such as carbon fiber and glues and so on and so forth. And so we're able to make things that are a lot stronger and lighter than a dragonfly wing, or maybe not as light, but very close to being that kind of mass. I think that if a dragonfly could express jealousy, they would look at our wings and say, where can I get a pair of those? So, there are advantages in the materials we've got, but, you're right, we have to go back to first principles and design every bit of it. But other things are also become very interesting in this domain. If you like, the control electronics package that has been partly responsible for the explosion of the drone market is available at a very small scale now. I think more as a consequence of what's happened in the mobile phone market than the drone market. I think the drone market is a beneficiary of the kind of MEMS devices that not that many years ago would have been too heavy for what we're trying to do and prohibitively expensive. So, there's a sort of sweet spot at the moment where we think that the available materials and sort of technology pack, if you like, is such that it's possible to do something like this now. I think it would have been very difficult to do 15 years ago.
In the movie Eye in the Sky, there's a small personal drone that looks like a horsefly.
Yes.
Is that the Hollywood equivalent of the technology you're talking about?
Yeah, I'd love to make that. I mean, I'm afraid that is CGI. I mean, yeah, that's the sort of thing that we're looking at. Although, if I remember correctly, in the film, that was a sort of beetle, and it had shell structures to protect its wings that came out. I mean, that is a complication you don't need to do.
Now, the Skeer drone was designed for military use. What were the requirements?
The requirement for it is very much what I was saying at the beginning, which is to have a highly gust-tolerant, small surveillance drone, if you like. What's happened in the field is that they've been using small drones and very successfully. It doesn't take a lot of imagination to understand why. If you're in a difficult situation under fire and you want to see what's around the corner or over a wall, it's useful to send something out to take a look. Of course, the thing that you send out, you want to be as discreet as possible because by sending it out, you could indicate your position. So having a small, stealthy, UAV is an extremely useful thing to have on the ground. However, the units that are being deployed at the moment have the problem that I outlined earlier, i.e., they get blown about by the wind. So they work perfectly when the wind is still, but the wind is not often still in places like Afghanistan. How do you manage a situation when it's blustery, or it might be still and then it goes out on a mission and then it gets blown into a bush, in which case you've lost your intel. So they came to us saying it was a very clear requirement. I mean, they knew about us. We understood that there was a problem. So we went to them and said, we think we can figure out how to solve that problem by taking a close look at a bio-inspired approach. And really, the discussion came from that. There are other pretty neat things about flapping wings as opposed to rotors, one of which is that they're really quiet. And the other is that you don't have a high inertia spinning mass. So as you probably know, if a rotor hits anything, you, generally speaking, break the rotor, particularly if you use, the current most popular design for sort of micro surveillance is a product called Black Hornet, which has been highly successful and is a beautiful piece of kit. It's a helicopter design, but of course, like a helicopter, it has a swash plate and tipping rotor blades. And if they hit something, they are quite delicate. Wings don't carry the same level of inertia, so they can bump into things and they're fine. In fact, in our lab, they flap away and you can put your finger in the flapping wings and they just carry on flapping, basically. So there's something quite nice about that, which is a sort of added benefit.
So have you already developed the mechanism to flap the wings, and does it provide enough lift to actually move something?
Yeah.
Wow, that's pretty amazing. Does the current model have a large set of wings, or do you have them down to the size that you're looking for already?
No, they're the size that we're looking for. There is a separate, an additional set of challenges working at that scale. And we wanted to make sure that we could work at that scale from the get-go. So that's what we've done. And it's interesting. Everything behaves slightly differently when you're dealing at sub-millimeter size components, including, I'm afraid, a lot of time crawling on all fours on the lab, looking for pieces of metal that have flown out of your tweezers.
Yeah, that's definitely one big challenge that most applications don't have to deal with.
Yeah.
In contrast to the movie Eye in the Sky, where the Hollywood drone was used for spying indoors and even sitting on rafters, the benefit of the Skeer drone is to allow troops in the field to see over buildings or hills and gain a broader perspective of the terrain.
That's right. The U.S. Army, Department of Defense, has got a public open call for what they call a soldier-borne sensor, which if you Google that, you can find the various presentations about it, which sort of outlines their requirement quite clearly. And the idea is that it's something that it's a kind of almost an everyman product that you can use for situational awareness.
Let's turn to the origin of the company for a moment. Is it true that Animal Dynamics started within the University of Oxford?
It did. It's a classic kind of spin-out company. In other words, so my background is an entrepreneur. I've started several businesses. Adrian's an academic through and through, and he's professor of biomechanics. Like many good things, the starting position was not in any way conventional. In other words, we didn't set out to do what we're doing now. We found that we were both interested in the same thing, which is just there's a sort of deep fascination in how natural systems work. And it turned out that we were both fascinated by the way fish swim, just something I happened to get interested in about 20 years ago and started playing around with because I thought it was so cool. And we got introduced by a mutual friend and just found that we were both fascinated in this set of problems. And we started building things, not a company. We started designing and building things that could use that piece of, if you like, nature's insight, which is extremely subtle, the way they do it. One doesn't realize that fish are, and insects are precision instruments in the way in which they exploit certain phenomena of fluid dynamics to get massive efficiency gains.
Now, this is going to go back a while, but isn't this approach similar to the rationale behind why Olympic swimmers changed their swimming style? If you remember, traditionally they would kick after making a turn. Then research suggested they could improve their swimming times if they swam more like a fish.
You're quite right, they do. And there's been some very clever insight. Some work from some US academics out of Ohio State University that figured out this sort of shark skin swimsuit, which is another application of bioengineering. But you're quite right, the swimming technique has changed a lot. Interestingly, a lot of the fundamental physics and fluid dynamics behind the way in which fish swim was done by a British mathematician called Lighthill, who had Cambridge's Lucasian Chair of Maths for Stephen Hawking. And his hobby was swimming. And out of interest, he wrote a number of papers explaining the fluid dynamics of fish swimming. And in fact, developed his own style of swimming, which was enormously efficient, based on his understanding of fluid dynamics, and used to swim around some of the Channel Islands for fun. An extraordinary thing. I mean, he would study the movement of the tides and then swim around ostensibly extremely dangerous islands using his knowledge of the tides and his very efficient form of fish swimming.
I think it's fascinating when different fields of study are leveraged to produce something brand new.
I've learned a lot through this process, and I now look at insects with a sense of total kind of hats off, man. What they're doing is totally extraordinary.
Now, you're primarily an entrepreneur. So when did you start looking at or becoming more exposed to how natural systems can be applied?
I've had a sort of an abiding interest, an amateur one, for a number of years, but I really sort of became hugely drawn into it as a result of meeting Adrian and doing some design work. We worked on a design which we're still working on, which is a human-powered vehicle where there is a flapping fin that will propel you very fast, and we're testing it out. In theory, we should be able to break the world speed record. And we've got this design which we've been working on, which in fact we worked on for a year and a half or so before we started the company, just as a project that we were kind of fascinated in. And it's something that we're still doing. But I mean, what's happened, of course, is that the Skeer project has become overwhelming, and we only have so many hours in the day to work on stuff. So we're kind of focusing on this for right now.
Can you describe the relationship between the company and the university? Was Animal Dynamics created to leverage the knowledge from the university into a commercialization of a product?
Not quite, because it's really a set of ideas that have been cooked up between Adrian and myself. So we don't have a call on the university's IP at all. And in fact, as an academic institution, the university is very, I think, correctly quite strict about that. They won't let any spin-out company have a call on that, because obviously that compromises the sort of academic freedom that is certainly more important than what we're doing in that respect. So it's more a case that Adrian's expertise and interest, I guess, combined with some business skills that I bring to bear, are resulting us in kind of just making things that have learned from a large body of academic study and his expertise.
You're really just a separate entity then. You're drawing research from the university, but you're not necessarily affiliated with the university.
Exactly. I mean, the university is a shareholder in our business. So we are, officially a spin-out. But like many institutions, the universities can see that there are interesting opportunities to create companies that have a relationship with the academic studies that are underway. And there's been quite a big sort of focus on that, I guess, with a number of British universities over the last, it's accelerated over the last few years. I mean, you may have noticed that there was a very large fund that's been set up to invest in Oxford University spin-outs that has some quite big name investors in it. It's called Oxford University Innovations. And so there is certainly an interest in making sure that there is a nice sort of ecosystem of businesses that are thriving off academic work. But all the time with this sort of, I think it's quite an interesting tension between the university's sort of academic ambitions, which need to be kept extremely independent, and a desire to see some sort of commercial and economic success out of that effort or related from that effort. It's very successfully done in the US, I must say. I've been exposed to that on a number of occasions. And I think the UK is learning from the US and maybe kind of a little bit behind the curve, but there's some interesting stuff going on now.
Yeah, that's very similar to what happens in the US when university research leads to a new idea. Rather than keep it within the university or lose it completely, a pathway is usually created so promising opportunities can make it to the marketplace without causing any conflicts with the university's primary mission.
We're in the thick of that. And that's exactly the kind of business we are, I think.
Where are you now on the Skeer drone? When do you think you'll have a prototype ready for testing?
Well, certainly next year we will.
Because it's for military use, will we, the general public, see it in action? Or because it is a military application, will we just know about it, but not necessarily see all the details?
I think we will hear about it. I mean, it is in the public domain now, more, somewhat to my surprise, I have to say, because the MOD decided to go public on it in August last year. I think there are good reasons for that, basically because everybody, including all the troops, have got mobile phones. The moment something like this is out there, people are going to video it. So that it'll be almost impossible to keep under wraps. They're quite cute as well. So they're amazing things to look at. There is something very endearing about seeing flapping wings. I can't really put a finger on it, but you just can't keep your eyes off them.
What has the process of creating the Skeer drone taught you?
This is a bit generalist, but I think that we've, through having to make a thing based on academic studies on how they work, and Adrian could speak to this obviously far more eloquently than I can, but we've learned far more about how insect flight works than we realized. It's very, very subtle. And the sort of, how should I put it, the envelope of possibility for flight, for insect flight in particular, is very narrow. In other words, lots of things have got to be just right for it to work, which is a remarkable thing, given how successful it is as a means of locomotion in the insect world. Things like the wing structure and the weight and the weight distribution and the balancing and all those factors are very, very subtle indeed. And so I think going to be very interesting going forward is that the kind of work that's happening, that we're doing, is going to, without doubt, result in some very interesting academic work re-looking at some of the assumptions on insect flight that have really only come out as a result of having to actually make something do what they do. And in my mind, that's probably one of the most exciting sides of it. But, from what we're learning as a company, I guess one of the biggest areas is getting to understand how to work with not nanomaterials, I'd call them kind of micro materials. So, and that's been extremely interesting. Building things at this scale is actually fascinating.
Does it require a whole new set of skills for someone to learn to work at that scale? Or do you think people coming out of universities today already have the skills to work at the micro level?
That's a very good question. I think that it's curious because it's a combination of skill and expertise. I mean, obviously, if you're good at the physics, you can work that out. But there are all sorts of tricks when you get down to that scale that you need to learn about. And also, there are skills, mechanical coordination skills. You're building stuff under a microscope. It's pretty hard to do that. So it's not just sort of, if you like, maths and physics and engineering skills. It's also craft skills are valuable when you're working at that scale. I am now not surprised that if you go and work for a Swiss watch company, there is a 6-year apprenticeship before you'll get let loose on a mechanism. It's really, really hard. So, I mean, to answer your question, kind of yes, definitely. And we are constantly on the lookout for skilled people. One of the comments I would make in terms of the sort of output from the sort of academic institutions is that what's happened over the last, I don't know, I guess it's almost a generation, is that the students have been more and more weaned off making things and weaned onto modeling things on computers. And a lot of the computational stuff is very, very useful. But it's a great pity that people are not encouraged to make things and also encouraged to learn how very, very difficult and unforgiving the world of making things actually is. Stuff looks beautiful in CAD, very often doesn't work at all when you try and make it. And understanding how to bridge that gap is something that is not being taught enough at the moment. And we're certainly noticing that in the people we recruit, that it's hard to find people who've got the kind of hunger to figure out how things actually work physically.
This movement towards micronization could very well be creating the new craftsman of the 21st century. Yeah,
and I think it applies in many different domains. I mean, of course, if you're involved in making sort of medical devices, miniaturizing those is important. And if you think of the really successful consumer electronics, they've all benefited from miniaturization. So it's certainly a high value area to go into and difficult and therefore worth looking at, in my opinion.
As we start to wrap up, Alex, what's your take on where the drone market is headed, and how will animal dynamics fit into that future?
I think there are several sides to the drone market that are interesting. I mean, there's obviously a lot of excitement about the platforms themselves that can move around and the sensors you can put on them. But I mean, the area that we're interested in longer term is really how they can be used, and how, if you have a platform that can go into different places, the value really that comes from that is the way in which you take the data from that platform and then build it in something that's really useful. And like many hardware businesses, their ambition needs to be in software as well as in hardware. And that's something that we're very actively focused on. Inevitably, if you're making things that move, you are making robots. And if you're making robots, there is a massive software component to it. I think that the certain sections of the drone market are going to become very rapidly commoditized in terms of hardware. And the really interesting area of growth is the software that stitches all the data together from that hardware.
And finally, as a successful entrepreneur, what do you feel is the key quality that someone should possess in this industry if they want to start a successful drone company?
A really important thing is to have a strong nose to figure out a customer need, because the technology itself is very seductive, and it's very easy to kind of get carried away with building something that does really cool stuff. But figuring out a customer need and working out how to fulfill that, it's classic business, I guess. There's no magic there. But I think a lot of people are beginning to realize how useful drones can be, and they need to find out, and you need to figure out how to tap into that. So, I was at the AUVSI show last week in Dallas, and of course, there's a lot of interest there in gathering and surveillance and so on and so forth. But I think there's some fascinating applications in agriculture and in sorting out some environmental issues and so forth. With the new technology, it's very easy to get carried away with the cool whizzy stuff and then lose sight of how people are actually going to use it and get value from it. I think that is those qualities that I think are most important.
That's it for episode 103 of the Drone Radio Show. I hope you enjoyed listening to Alex Caccia of Animal Dynamics and learning how researching high-performance animals can lead to improvements in performance. I want to thank Alex for taking the time to speak with me. If you want to learn more about Animal Dynamics or want to connect with Alex, check out the website at animaldynamics.com. If you like the Drone Radio Show, please consider supporting the podcast with a small donation. The content is always free, but for as little as $1 per month, you can help defray the costs of productions. To donate, go to patreon.com/Drone Radio Show. Thanks for listening. Your support means a lot to me, and I hope you'll listen to more episodes of the Drone Radio Show podcast to hear how others are using drones for business, fun, and research. For the Drone Radio Show, I'm Randy Goers.
This has been the Drone Radio Show podcast. More information on today's show can be found on our website at www.droneradioshow.com. If you're using drone technology for business, fun, or research and would like to share your experience on the show, please visit our website and fill out a guest appearance application. And don't forget to follow us on your favorite social media channels.